work is equal to scalar product between force acting on the body and its displacement. The scalar product is also called a dot product, which is certainly a parallel component of force times displacement, and in this formula, these two terms are scalar quantities. If we take scalar displacement and scalar force, then we have to take into account only the component of the force which is parallel to the displacement, which is the same, which is equivalent to a dot product of two vectors. Is it the law of physics, or is it not the law? Who knows? Is it the law? A fundamental law of physics? No, this is not the law of physics. This is just a definition of physical quantity, which we call work. We can invent as many definitions as we want. We may invent different quantities, well, anything you like. For example, you can invent a quantity like a square root of the speed. Okay, you can invent it, you can define it, you can define a formula, you can call it any name you wish, like, well, let it be something like, well, watermelon. Okay. We call it watermelon, and we invent this quantity. Do we have the right to do so? Certainly. But will such quantity be of any use in solution of any practical problem? I doubt so. No, this will be useless quantity. It will add nothing to your capability in solving different problems. So many quantities can be invented and introduced, but only a few of the quantities are of any use. And the quantity of work is very useful. It can help you solve many problems, really. So this is not a law of physics. This is just a definition, but the definition of such physical quantity which is very useful. Also, we obtained another formula which establishes the connection between work and kinetic energy. The work produced equals the difference in final and initial kinetic energies of a body of mass m. So final kinetic energy minus initial kinetic energy. That's the work produced by forces acting on the body. There is some difference between these two formulas. In the first formula, force F can be any force acting on the body. It may be a separate force, or it may be a net force, that is a vector sum of all forces. Anything. You can discuss the work produced by a separate or single force acting on a body. If there are many other forces, we just don't pay attention to other forces. We calculate work produced by a single force, which we are interested in. Yes, that's quite possible. But in this formula, work A is produced by a net force. That is the total force, the resulting force, the sum of all forces, vector sum of all forces acting on the body of mass m. And only if this is a net work produced by net force, only in this case such work equals the change in kinetic energy of the body, which takes place during some time interval. Also, another important thing which we discussed last time was the law of conservation of mechanical energy. If we denote the total mechanical energy of a system of bodies, then this quantity will be constant in time. Where the total mechanical energy is potential energy plus kinetic energy of the system of bodies. Does this law hold in any situation? No. Sometimes and very often this law is violated. When is it violated? When we have forces of friction or so-called dissipative forces, friction or resistance of the medium or air drag, etc. In this case, when you have dissipative forces like friction, then the total mechanical energy will not be conserved, because in the friction, in the process of motion, if friction is there, some of the mechanical energy is dissipated into heat. Because of friction, the bodies are heated, their temperature is increased. And so mechanical energy is transferred into a heat energy. Some part of mechanical energy is lost or dissipated. That's why the law of conservation of mechanical energy works only if you have no dissipative forces, no forces of friction, no forces of air drag or resistance of medium, like resistance of a liquid in which the body is moving. So this is a very useful law, but it works in limited number of situations. Actually, it never works, because forces of friction are always there, and forces of like air resistance are always present. But sometimes they are very small in comparison with other forces. Sometimes forces of friction can be neglected, and then the law of conservation of mechanical energy will work and will be very accurate and will produce very precise results of high degree of precision. But we must understand that forces of friction to some extent are always present in whatever situation you consider, except for some processes taking place in deep space where the concentration of molecules is very small in outer space, when in very good vacuum, when you have no medium and practically no resistance, no friction, then this law will be very, very precise. But even then, even in vacuum, we must understand that the vacuum is not always ideal. There is always some small concentration of molecules, even in the cosmic vacuum. So strictly speaking, it's impossible to create a process which is accompanied by no friction. It's practically impossible. There will always be some very small friction, but negligible. So small that we can neglect it. And then this law can be used. Okay, we have discussed all these things, all these issues during the last lecture, and now we will solve more problems to learn how these laws of physics can be applied in a solution of different problems. First problem will be number 125. A box with sand having the mass m is suspended on a rope with a length L. So there is a rope or a string of length L, and there is a box of mass m hanging on the string. The length of the string L is much larger than the linear dimensions of the box. So the box can be considered small. All its dimensions are small as compared to the length of the string. A bullet of mass m, flies in horizontal direction, strikes the box, and gets stuck in it. After this, the rope is deflected by angle alpha. So the bullet strikes the box and gets stuck inside it because the box is filled with sand, according to the statement of this problem. And after that, the box starts moving, and it moves to some new position, which is maximum displacement, so that the string is deflected by angle alpha from the vertical, from its initial vertical position. Determine the velocity of the bullet. What we need to find the velocity of the bullet in this situation. This is a real experiment which is often carried out in order to measure the velocity of a bullet. It's one of the simplest ways to measure the velocity of a bullet. If you invent some new type of gun, then the first thing you measure the velocity of the bullet. So this is the very real procedure to measure the velocity, because it's easy to fire a bullet into this box and then measure the maximum angle of deflection, because the box will be deflected and then will go back, and then it will somehow be oscillating here to and fro. But the maximum angle of deflection will give you the information about the velocity of the bullet. So how do we solve this problem using the laws of conservation? Not only conservation of energy, but also conservation of momentum. Let's consider all the processes which take place here. Originally, the bullet had momentum equal to mv, the momentum of the bullet directed horizontally. And then the bullet hits the box and gets stuck in it. This process takes very little interval of time. Such a small interval of time, because the bullet flies at high velocity, hundreds of meters per second. And so when it stuck in this material, it penetrates the box with the sand just by a few centimeters. And if the bullet goes at the velocity of, well, say about 1 kilometer per second, for example, just approximately, and it stuck, it's retarded, and it stops covering the distance of, say, 10 centimeters, then what time does it take for the bullet to be stopped? Less than 1 millisecond. Very small interval of time. So the duration of time when the bullet is retarded here, the duration of time is approximately by the order of value. The length, which is covered by the bullet inside the sandbox, the length divided by the velocity. And this is by the order of magnitude. Well, if the length is, say, 10 centimeters, that is 10 to the minus 1 degree meters, and the velocity is about 1 kilometer per second, 1,000 meters per second, then that will give us about 10 to the power of minus 4 seconds. That is 0.1 milliseconds. A very short period of time. This is not not a strict calculation, but a calculation of the order of magnitude. We just approximately evaluate what this quantity may be, whether it's large or small. And we can easily estimate that it's less than 1 millisecond. Less than 1 millisecond. And during such a short interval of time, the box, the heavy box of sand, will not shift at a large distance. It will be practically will remain at the same position. The box may shift just by a very little distance. So we may conclude that during such short interval of time, no additional forces will act on the system. If the box was deflected by a large angle, then there would be forces of gravity that should be taken into account. But if the box has no time to be deflected at a large angle and remains practically where it was, then we don't have to take additional gravitational forces here. The position of the box remains here where the gravitational pull is balanced by the string tension. If these two forces are balanced, then we may conclude that no other forces are acting on the system. And in this particular case, the law of conservation of momentum holds here. The initial momentum must be equal to the final momentum. The initial momentum was mv, and final momentum of the system will be total mass of the box with the bullet inside it times final velocity times final speed. A law of conservation of momentum can be applied when no external forces act on the system of bodies. Only internal forces are present here. In this case, the momentum of the system is conserved. What is the system here? The bullet plus the box with the sand. That is the system of two bodies. And its total momentum must be conserved in time. The initial momentum before the bullet strikes the box, and the final momentum after the bullet got stuck inside the box, so that the total mass of the body is the sum of mass of the box and the bullet, and they have the same velocity. The bullet and the mass and the box have the same velocity. From this, we can easily calculate the final velocity of the box with the bullet inside it. The final velocity will be m over capital M plus lowercase m times the velocity of the bullet. That will be the initial velocity of the box after the bullet, I will show it in this way. The initial velocity, well, it's very small, but I draw the long vector so that it will be easier to discuss the situation. Actually, it's very small because the mass of the box is much larger than the mass of the bullet. And so if the mass of the bullet may be, well, like about 10 grams approximately, and the mass of the box may be several kilograms. So the denominator in this fraction may be about 1,000 times larger than the nominator. So the velocity u may be approximately 1,000 times less than the initial velocity of the bullet. The difference is about 1,000 times. But let me draw such a long vector just to facilitate the consideration of this problem. Sometimes we have to draw vectors and displacements somewhat unreal, somewhat enlarged, in order to make the picture more clear. If I draw here a very small vector, it would be unclear and it would be difficult to solve the problem. So I make everything for the problem to be clear, for the solution to be clear. And so the length of these vectors do not correspond to the actual quantities of these, actual values of these physical quantities. So we have, after the bullet got stuck inside the box with the bullet starts moving with this velocity. And all this happens during very small time interval. And then the box, as a heavy object, moves slowly with this velocity, and then it stops, and then it starts oscillating on a long string. This period of oscillation may be measured in seconds. It takes seconds. It's obvious. You can do this. You can choose a long string and an object and see how long it takes for a period of oscillation. It may take seconds. So the period of oscillations may be hundreds and even thousands times larger than the time interval of interaction of bullet with a sandbox. So the interaction of bullet with a sandbox is much, much smaller than the period of further oscillations. That's why we can apply the law of conservation of momentum. So after the bullet has stuck in the box, this object starts moving with the velocity u. What happens then? If it has some velocity, it has some kinetic energy. And it moves in gravitational field of the Earth, where we have a potential energy of bodies, gravitational field. We don't take into account forces of air drag. They are very small, certainly because the box is heavy. If you try to move a very light body like feather in the air drag will be very noticeable. But here, if the box is very heavy, then the air drag forces are negligible in comparison with the gravitational forces and forces of the string tension. So a law of conservation of energy, mechanical energy, may be applied on this stage of the process. After the bullet got stuck and the box starts its motion, the law of conservation of energy, mechanical energy, can be applied here. What this law says, that the total mechanical energy is constant, and total mechanical energy is potential energy plus kinetic energy. Let's use this law here. Potential energy, well, the velocity is a small letter lowercase letter, and the potential energy is U uppercase. It's uppercase potential energy, so that we can easily distinguish between the two quantities. Velocity is lowercase, and this is uppercase letter. So the potential energy is mass times g, acceleration of free fall, times the height. Total mass is the mass of the box and the bullet stuck in it. GH. What is h? The height of the box with respect to any level which we choose for convenience. We may calculate h, the height, starting from any initial level, from here. But it's obvious that most conveniently the height should be calculated, should be measured with respect to the initial position. If the initial height was 0, then the initial potential energy is 0. It's much easier, much more simple equations. So the initial potential energy is 0 because we choose the level of 0 height coinciding with the center of mass of the box and the bullet before they are deflected. But we may choose any level if we want. So after the box is deflected, its center of mass will go up at some quantity, and that will be the height of the center of mass with respect to the 0 level, initial position of the center of mass. So as the box is deflected, the height of its center of mass increases, and so the potential energy increases. The potential energy and the kinetic energy must remain constant in time. So we may use this equation: the initial potential energy plus initial kinetic energy must be equal to final potential energy plus final kinetic energy. Initial means at the beginning of motion, when the box was here at rest in the position of equilibrium, when all the forces acting on it were balanced. That is the initial position. What is the initial potential energy? Initial potential energy is 0 because the initial height h is 0. What is the initial kinetic energy? Initial kinetic energy is not 0 because the velocity, there is some velocity with which the body moves in the beginning. So the initial potential energy will be equal to total mass, which is mass of the box and the bullet, initial velocity u squared over 2. Final potential energy will be equal to what is written here: total mass of the box and the bullet inside it, GH, and the h is some height of the center of mass over the 0 level, 0 position. And the final kinetic energy will be what? Finally, the box moves to its maximum deflection position. This is the amplitude of oscillations, and at this point the box stops and starts moving backward. So at the maximum deflection the velocity is 0. It changes in its site. So final kinetic energy is 0. And therefore we get this equation. We obtain that this term must be equal to this term due to the law of conservation of energy. So on the first stage of solution, we took into account and we used the law of conservation of momentum. And on the last stage, we used the law of conservation of energy. Why so? Why not vice versa? You must be able to explain it. Because the conservation of momentum holds when no other forces, no external forces act on a system of bodies. And the law of conservation of energy holds when there are external forces, and these forces perform work. But we neglect forces of friction, we neglect forces of air drag. So on the last stage, when the box starts moving, we can use the law of conservation of energy. But on the first stage, when the bullet gets stuck in it, in the box, we must use the law of conservation of momentum. And the energy, mechanical energy, is not conserved on the first stage, because the bullet strikes the box and gets stuck in it, and when the bullet is retarded here, there are very huge forces of friction. And actually, a good part of initial kinetic energy of the bullet will go into heat. All this, the sand and the bullet will be heated. The temperature of the bullet will increase. And if you take the bullet immediately after it was stuck in the sand, you can drop your hand here and find the bullet and take it. It will be hot. You will see that the bullet is very hot. Its temperature may be very considerable because of the forces of friction here. Well, so part of kinetic energy of the bullet is lost because it's dissipated. It goes into heat of the bullet and surrounding medium. And the mechanical energy is not conserved during the first stage, but law of conservation, but the momentum is conserved, and the law of conservation of momentum holds. But on the second stage of the process, momentum is not conserved. Momentum of the system is not conserved. Why? Because external forces act on it. Here at this position, a force of gravity and the force of tension in the string, and they act at some angle, and there is a net force, or a vector sum of these two forces is not zero, so there is some external force from outside bodies is acting on the system while it's oscillating here. And so when external forces act on the system, the law of conservation of momentum is not valid. It's not applicable. But the law of conservation of energy applies, because forces of friction and air drag can be neglected. So from the equation, equality between these two terms, we can easily find that the velocity u squared equals 2gh, and the mass is cancelled. And the velocity u squared is related to the velocity of the bullet. So we can take this expression for the velocity of we can take this expression containing the velocity of the bullet and substitute it here for the velocity u, and then we obtain m squared v squared. I take this expression over capital M plus small m squared. Our purpose is to find the velocity of the bullet, and all our calculations go in this direction. We must finally express the velocity of the bullet through other quantities given in the problem, in the statement of this problem. So from here we can find the velocity of the bullet squared. It's capital M plus small m over m squared by 2gh. That's the velocity of the bullet. Is it the final answer to the problem question? No, because the final answer must contain only the quantities given in the problem. Masses are given, but h, the height is not given. Instead of the height, the angle of deflection is given, alpha. So we must find a connection between h and alpha. This connection is easily established using geometrical considerations. So the center of mass of the box goes along the circular trajectory because the string is unstretchable. The length of the string remains unchanged as the box moves here. Is it always true? No. There are no absolutely unstretchable materials. Any material can be stretched a little bit, but sometimes this change in length is very, very small and negligible, and we neglect it. We assume that the string is unstretchable, and that is a very good approximation. But we must always keep in mind that this is just an approximation. Almost everything in physics is an approximation. Almost everything. So we draw a parallel line from some point in the circle, and we know that this section is h and this is L, the length of the string, the same as here. And so if we consider this right triangle with the right angle, in this right triangle we can find the leg adjacent to angle alpha, the leg adjacent to angle alpha, this leg of the triangle. Let's denote it as A, and another leg may be B. Then we know that A divided by L, the adjacent leg divided by L, is cosine alpha. By definition of cosine, this is not a law of physics. It's not a law of mathematics. This is just the definition of mathematical function cosine. You should always know where you deal with definition and where you have a law of physics. The definition is absolutely accurate because we define it in this way. We have defined it. This is absolutely accurate. There is no approximation here because we define the quantity in this way. But when we use this quantity in the law, then we get some approximation because we neglect, we always neglect some small quantities. So this is by definition, and we know what is A. If we know what is A, then we can easily calculate H. H is L capital, the whole length of the string, minus the leg of this vertical leg of this right triangle. So H can easily be calculated here from here. This is capital L minus L cosine alpha, which I find from here, from this equation. A is from here L multiplied by cosine alpha. So we can take L out of the brackets and write down L multiplied by 1 minus cosine alphas. That is the quantity h, which was unknown so far. Now we can use this expression here. We can substitute this quantity for h in this formula, and finally we can obtain that the bullet velocity squared is this expression squared times 2gh, and h we have just calculated. It's L 1 minus cosine alpha from geometrical considerations. We have found h, the height to which, the maximum height to which the center of mass rises of this box. So in this formula, everything is given in the statement of the problem. Masses are given, acceleration of free fall, the string length, everything, and alpha is given. So everything is known from the statement of the problem, and all these quantities actually can easily be measured in an experiment. If you carry out such an experiment to determine the velocity of the bullet, you can easily measure the mass of the box with the sand, and the mass of the bullet, and the length of the string. Everything can be measured beforehand, and during the experiment you have to measure the angle of maximum deflection of the string. So this formula will give you the velocity of the bullet. It will be m plus m over m square root of 2gl 1 minus cosine alpha. And the only thing remaining, if you carry out this experiment, you have to measure the angle of deflection of the string and then substitute all the quantities here and calculate according to this formula and obtain the velocity of the string, of the bullet, the velocity of the bullet. Now we have come to an important stage in a solution of any problem. And I have not yet discussed this issue before, but now I think it's a good time to discuss it. Whether this solution is correct or not, how can we prove that this formula is correct? Sometimes people make mistakes. Sometimes people make algebraic mistakes. I could have missed something here. I could have made some simple mistake just by neglect, but the final formula, I must be sure that this is correct. How can I be sure? First of all, I can certainly look through all the calculations and then establish the correctness of this formula. But there is a much simpler way. We can analyze the correctness of this formula by just looking into the formula and thinking about how do these quantities influence the velocity. For example, if alpha is larger, for one bullet, the alpha is larger than for another bullet. And the two bullets are identical, but just they have the same mass, but just were fired from different guns. Well, the same, actually two identical bullets having the same mass in the same experiment with the same sandbox. Well, we fired two identical bullets from different guns, and so we expect the velocity to be different, and the alpha will be different. If angle alpha is larger, then what will this formula give us? If alpha is larger, then the cosine alpha. What is cosine? We know if alpha is 0, cosine is equal to 1. And then cosine goes like this. And for alpha equal pi over 2, this is 0. So for larger alpha, we get smaller quantity of cosine, and the difference between unity and cosine will be larger. The larger the angle alpha, the larger will be the difference between the larger will be the value of this round bracket. So if alpha is larger, then this quantity will be larger, and hence the velocity larger. Is it reasonable? Certainly. The larger the velocity, the more will be the deflection of the box. The larger will be the angle alpha. So this is quite reasonable, seems to be good. If it were something like, well, some different function, for example, sine instead of cosine, then it would be against the reason, against the logic, because the sine grows with the angle, and 1 minus sine will be smaller if angle grows. And so we will obtain with the sine, the formula would give smaller velocities for larger angles. That's unreasonable. We understand from intuition that the larger the velocity of the bullet, the larger will be the deflection of the box. So just analyzing this formula, we can see that it looks like reasonable. It looks like correct. Another thing is, for example, the mass of the bullet. If we take another bullet, a different one, with smaller mass, the mass will be smaller. Then the smaller thing added here will change practically nothing, because this is about 1 kilogram or even more than 1 kilogram, and the bullet is just a few grams. So the smaller bullet will not change drastically the numerator, but the denominator will be changed. If the bullet is twice as small, then the denominator will be smaller, 2 times smaller, and the whole fraction will be 2 times larger. So if all other parameters remain the same and the mass of the bullet is smaller, then the velocity will be larger. Is it reasonable? Yes. Yes, it's reasonable, because you need larger velocity to ensure the same angle of deflection if the mass of the bullet is smaller. This is understandable, this is reasonable, this is in comfort with our intuition. So analyzing the final formula gives you ample opportunity to establish whether the formula is correct or not. If you make some mistake in the formula, most probably it will become unreasonable. The formula will become against our physical intuition. So that is the first one of the simple ways to establish whether the formula is correct or not. If it's not correct, then it will go against the intuition and against the sense of the reason behind the events. Another important thing is to consider the dimension of this formula, that is, the units of measurement. So if we substitute units of measurement here, kilograms for mass, and the known quantity for g, which is measured in meters over second squared, and L is measured in meters, and we substitute here the units of measurement, then we know beforehand that we must obtain the units for velocity. That is, we must obtain meters over second. Let's check it. If we substitute here kilograms, they will cancel, kilograms will cancel, and here the acceleration meters per second squared times length is measured in meters. So what we have here, meters squared over second squared, and we take the square root of it. So finally we will get meters divided by seconds. That is what we must obtain. So the formula produces correct units of measurement. If we check the units of measurement, then this is another way to find a mistake, a possible mistake in the formula. If you make a mistake, most probably units of measurement will be broken. They will be wrong. If you make a mistake in your calculations, the units of measurement will be something different. It will not be a velocity, it will be something different. So when you solve any problem in physics, any problem, you must always do these two simple steps in the end of your solution. When you obtain the solution, you must do the following. First, you must check the units of measurement, whether your formula gives you the desired units of measurement of your physical quantity which you are looking for. The units of measurement must be correct. If the units are not correct, then there is sure to be a mistake in your final formula. And second step, you must analyze the formula for physical sense. You must analyze whether the formula conforms with your intuition, with what is going on in this physical process which you consider in the problem. So analyzing measurements, units of measurement, and analyzing the formula for its whether the formula is reasonable or not. That's it. You must analyze it. The two steps you must do always. You must always do whether you solve a simple problem in physics or a complicated problem in chemistry or even more complicated in biology or anything. You must always do these steps. You must always check the units of measurement of your final formula and if it's reasonable or not. So, I gave this problem a very detailed consideration, and that will not always be the case. Sometimes I will present you a quick solution of some problems, but at least one problem should be given such a detailed consideration. Any questions? Everything's clear? Okay. So we have considered a very realistic situation related to the measurement of the velocity of a bullet. And actually, the velocity of the bullet is very often measured using this particular method. And the next semester, you will have physical laboratory as one of your classes. You will have lectures and seminars and work in physics laboratory. And there you will perform some experiments in mechanics. Next semester, the mechanics, you will study mechanics. The course of mechanics that you will study next semester will be different from what we consider now, because now we consider everything in the simplest possible way. But next year, we will use calculus. We will consider more complicated problems which require calculus. Differentials and integrals. Such will be the tools of solving problems next semester. So we will actually consider the same course of mechanics with the same laws of physics, but the level of consideration will be more complicated. We will use calculus. And also you will go to physical laboratory, and there you will perform some different experiments, including the experiment on measuring the velocity of a bullet. There is such an experimental setup in our laboratory. In physics laboratories, we have more than 100 experiments experimental installations prepared for you, more than 100 in mechanics, in thermodynamics, molecular physics, and electricity and optics and atomic physics altogether. You will have the possibility to learn more than 100 experiments. So the next problem we consider will be let's beat let it be this one. Number 134. How should the power of a pump motor change for the pump to deliver twice as much water in a unit time through a narrow orifice? Disregard friction. So we have a pump which pumps water. So we have a reservoir of water. There is some water in the reservoir. And there is a pipe and a pump. And the pump, what pumps usually do? They pump water to some height, and then water runs from this orifice, small orifice with some velocity. So the pump takes water from this reservoir and lifts it to some height. This is actually what the pumps usually do. How should the power of a pump motor change for the pump to deliver twice as much water in a unit time through a narrow orifice? Disregard friction. It seems to me the statement of this problem is not complete. Something is missing here from the statement. And what is missing, we will now discuss. So we have a pump which pumps water, and in a unit time, some amount of water goes here. Let it be delta AM, the mass of water which is pumped during time delta T. It may be a unit time, it may be 1 second. So some delta AM kilograms of water are pumped here, and they flow, the water runs here from this orifice with the velocity v. So we immediately know that the water of mass AM going with velocity v has the kinetic energy delta mv squared over 2. That is the kinetic energy of the water pumped within a unit of time, within 1 second, for example. So where does this water obtains its kinetic energy from? It gets the kinetic energy from the pump. The engine of the pump works and produces some work and spends some energy, and so the water obtains some velocity because it's pumped, it's pushed by the pump. But also the water goes to some height h, because usually pumps pump water to some height. It's no sense, practically no sense pumping water here, because this is the reservoir. What's the use of pumping water here inside the reservoir on the same level? No use. We must lift the water to some height, h. And so the same amount of water which is lifted during 1 second will increase its potential energy by delta AMGH. That will be the increase in potential energy of mass delta AM of water. So what the pump does, it increases the potential energy of some amount of water, and it increases the kinetic energy of the same amount of water. Naturally, the pump does these two things. So the work produced by pump in a unit of time, in 1 second, for example, the work produced during this small interval of time will go to increase the potential energy and to impart some kinetic energy. It's natural to put delta here, but no problem. Let it be this way. The water increases its potential energy and also increases its kinetic energy, because the initial speed of water here was 0 inside the reservoir. Inside this reservoir, the initial speed of water was 0, but final speed may be very large. So what is given in this problem? That at first the pump delivered certain amount of water per unit time and performed certain work and certain amount of water having some kinetic energy. And then the amount of water changed, and so the work produced by the pump in a unit time also changed. The potential energy difference is the same, but the kinetic energy will be different because the mass is different, and the velocity will be different because more mass must flow through this orifice in a unit of time. If you press, for example, 1 kilogram of water, 1 liter of water, it will have a certain velocity. But if you pump 2 liters of water during the same period of time, the 2 liters of water will have to flow through the same pipe and go out through the same orifice, and so the velocity must be 2 times larger if you have a larger amount of water, like 2 liters against 1 liter. So when 2 liters go from here, the velocity must be twice as that for 1 liter going from here. That's obvious. So if the pump starts pumping twice the amount of water, then it means that the amount of water in liters increased 2 times, and the velocity also increased 2 times. And that means that the kinetic energy of the increased amount of water will be different from the initial kinetic energy. K2 differs from K1. By what factor? The mass is increased twice and the velocity also is increased 2 times, but the velocity is taken squared. So 2 times increase here will give you 4 times increase in the square of this quantity, and multiplied by 2 times increase in the mass. So the final kinetic energy will be 8 times more than the initial kinetic energy. It follows from these 2 obvious expressions and from this formula. Right? Delta m is increased by a factor of 2. Velocity is increased by a factor of 2. Squared, when squared, we get the factor of 4. 4 times 2 gives you a factor of 8. So if the pump starts pumping twice the amount of water per unit time, then the kinetic energy of the water flowing from here will be 8 times more than the initial kinetic energy before the increase of the pump power. So what we have here, the work produced by a more powerful pump will be expressed through the same change in kinetic energy, the same quantity as here, because the height has not changed, and 8 times the amount of initial kinetic energy. potential energy is the same, but the kinetic energy increased 8 times as compared to the initial pump power. And the problem says, how should the power of a pump motor change for the pump to deliver twice as much water in a unit time? How should the power change? So we must calculate how much delta A2 must be larger than delta A1. Is it possible to conclude how much larger this quantity is as compared to this quantity? It's impossible. It's impossible because we know nothing about the first term in this equation. We know nothing about the first term, the change in potential energy. We know nothing about it. The problem says nothing about it. Why? I told you from the very beginning that the statement of the problem seems to be incomplete. It doesn't provide all the necessary information. We know nothing about the height to which the water is pumped, so we know nothing about the change in potential energy of water. Consider two different situations. Consider the first situation when the change in potential energy is much greater than the kinetic energy of water. That means that the pump is pushing water to a very high building, to a large height, and the velocity of water is just very slow, just water flowing slowly. Then in this expression, the first term will be much, much larger than the second term. And here again, the first term is much larger than the second term. The second term, being very small, may be neglected. And then we will obtain that the power of the pump practically remains the same, because it's lifting the water at the same height, to the same height. And the power will remain the same, delta U here and delta U here, plus some small, very small quantity, which is negligible. By assumption. We assume that the height is very large and the velocity is very slow. We assume this situation to be true. In this case, in this first case, under our assumption, the work done by our pump will be practically the same. Will change just a little bit, by 1 or 2%, 3%, 5%, doesn't matter. It will change by a small quantity. So the power of the water pump will remain practically the same in the first situation. Now let's consider another situation when the height h is very small, so that the first term in this equation is negligible. The height is small, and the first term here, the first term is negligible. It may be omitted. The first term is very small as compared to the second term. So the change in potential energy is small as compared to the kinetic energy of water. It means that the height is small, just, well, take it 1 meter. And the kinetic energy is very large because the water flows at very high velocity, In this particular case, the first term may be neglected, and then we obtain that in this situation, the second situation, we obtain that delta A2 will be equal to 8 delta A1. So if the potential energy of water can be neglected, then the power of water pump must be increased 8 times. Must be 8 times more than it was initially. So in two different situations, we get two different answers. And in any intermediate situation, the answer will be something in between the same power or 8 times the initial power. in any real situation, the answer will be somewhere in between. Why? Why such a large discrepancy? Because the statement of the problem does not provide enough information, no information at all about the height to which the water is pumped. We don't know the height. It's not given. And I consider it to be it's not very correctly formulated problem. It should be, something should be said about, something should be clarified about the height. Otherwise, it's impossible to give a final answer. It's impossible. We can give the final answer just like this, that the water pump power should increase by 8 times. But this will hold only in certain situations when the height is very small. The potential energy change is very small in comparison with the kinetic energy. Then the water pump power should increase by 8 times. Only in this particular situation. In any other situation, the answer will be different. Any questions? Is it clear? Actually, this is a very good collection of problems. And if you could solve any problem from this collection, that would be excellent. But some problems are formulated a little bit, formulation is a little bit incomplete. Something is missing. And also the translation into English is not always perfect. You can see it. But anyway, collection of problems is very good. Oh, let's consider this one. Another problem. Two plates whose masses are M1 and M2, problem number 142. Two plates whose masses are M1 and M2 respectively are connected by a spring. So we have one plate of mass M1. It's connected by a spring with another plate whose mass is M2. And the second plate lies on the surface of the table. Two plates whose masses are given, M1 and M2, are connected by a spring. What force should be applied to the upper plate? What force should be applied to the upper plate for it to raise the lower plate after the pressure is removed? Disregard the mass of the spring. So we press on the upper plate with some force, and the spring is compressed. And then we release the upper plate, and it springs up so that the lower plate jumps a little bit up from the surface of the table. We need to calculate the force which is required for this, for the lower plate to be separated from the surface. Certainly, if we press just a little bit, then the center of mass of this plate will go down just a little bit. And if we release the upper plate, it will go up because the spring will push the upper plate, and it will go up, and it will pass the original level where it was originally at rest, and then it will go a little bit up, and then it will oscillate about this position of equilibrium. At first, the upper plate was in equilibrium. At first, the weight of the upper plate, M1G, was balanced by the force acting from the spring, that would be T. The force acting from the spring and the weight were in equilibrium. The weight is directed downward and the force acting from the spring is directed upward. At first, the upper plate was in equilibrium. If we press a little bit, it will oscillate here about the position of equilibrium, but the lower plate will remain on the surface of the table. And the problem asks, what should be the force of pressure upon the upper plate so that when we release it, it will oscillate to such an extent that the lower plate will jump a little bit from the surface of the table. A good problem, which can be solved in different ways. It can be solved using energy considerations, but it can also be solved using just simple force considerations. First of all, let's pay attention to one simple fact, that the spring originally was compressed by the weight of the first plate. If we remove the first plate, the spring will go up, the length of the spring will be larger, it will be something like this, if we remove the upper plate. But if we attach the upper plate to the spring will be compressed by some distance a. And we know that the coefficient of rigidity of the spring times a, the compression amount, is the force with which the spring reacts to such compression, and it's equal to the weight of the first plate. So what will happen if we move the first plate down by the same distance a? If we move the plate, the upper plate down by the same distance a, then, and release the force and release the action, then the spring will increase its length, it will be stretched, and it will push the upper plate backward, and the upper plate will start oscillating here. The maximum height to which the upper plate will rise will be equal to the same distance a to which we have descended the upper plate. So if we move the upper plate by the same distance a, then it will be oscillating between about the position of its equilibrium between these two positions. And the upper position will correspond to the uncompressed state of the spring. In the upper position, the spring is uncompressed. And so the spring will not act with any force on the lower plate. And the lower plate will not, in no way will not be lifted by the spring. If we move the upper plate by the amount A, which is defined by the weight of the upper plate. So we must move the upper plate further and compress the spring even more to some larger distance. We must compress the spring something like that by additional quantity B, so that the upper plate starts oscillating between the lower position and the upper position, which are at equal distance from the equilibrium position. So this distance, the lower distance, will be A plus B, and the upper distance will be A plus B, because this is A, this is A, and this is A, and this is B. So we must press further upon the upper plate so that it goes lower. It goes at a distance a plus b. And the b must be such that the extension of the spring by distance b gives the force equal to the weight of the lower spring. That is distance a, and that is additional distance b. It must be so large that the spring, extended spring, lifts the lower plate. And it happens when the elastic force of spring deformation, which is k times displacement, equals the weight of the lower plate. Then the extended spring will be able to lift the lower plate a little bit from the surface of the table. That's it. Again, if we move the upper plate by distance a equal to a normal deformation of the spring under the weight of the upper plate, then the upper plate will oscillate about the equilibrium position between these two positions, and the upper position will correspond to non-stretched spring. Non-stretch, it means that no force will be acting on the lower plate. But we need certain force. That is why we have to move the upper plate to a larger distance at additional distance b, so that the total displacement of the upper plate will be a plus b, and so the displacement upward from the position of equilibrium will be also a plus b when the upper plate starts oscillating here. And this additional distance b is should be related to the weight of the lower plate, so that the spring could be able to lift the lower plate from the surface of the table. So these are two equations which give the answer to our problem. What force should be applied to the upper plate? The force should be equal to the spring rigidity times displacement times the deformation, amount of deformation of the spring. And from these two equations, it must be m1 plus m2 times g. If we act on the upper plate with such force and then release the upper plate will start oscillating, and in the upper position the spring will be stretched to such an extent that the lower plate will jump a little bit from the surface of the table. That's the final answer to the problem. It seems to me that such reasoning based on forces is somewhat simpler in this particular problem, is simpler than the energy considerations. We can certainly, in this problem, consider change in potential energy of the upper spring and the kinetic energy, and take into account all these energy changes, but the consideration based on forces is much springer. Look how short is the solution. Look how simple as far as formulas are concerned. You must just understand one thing, that when the plate is oscillating on the spring, its motion is symmetric. The way it goes downward equals the way it goes upward. And the motion is symmetric only because the force needed to stretch the spring is directly proportional. The force is directly proportional to the amount of deformation. If you have this deformation, then the force is proportional to deformation. Because this function is linear, only because of this fact, the oscillation will be symmetric. The oscillation of the upper plate will be symmetric with respect to the central position of equilibrium. If this function is nonlinear, something like such function, then the oscillation will not be linear, and then the displacement downward will not be equal to the displacement upward. And in this case, such a solution would be inapplicable. Okay, on this point, let us finish this lecture. I wish you good luck.